We've begun to study electric fields, and we started off with the definition of an electric field and then extended that to write down an expression for the electric field due to a point charge. And now we'd like to go into the discussion of electric field lines, which is a qualitative way of indicating the strength and direction of electric fields. At the bottom of the page you can see three diagrams. One that shows electric field lines for a positive point charge, the second that shows electric field lines for a negative point charge, and the third that doesn't show a charge but shows parallel field lines. And this is the right way to draw uniform electric field lines that correspond to an electric field that has the same value and direction everywhere in space. So how do we draw these diagrams? Well, there are some simple rules for electric field lines. First of all, what do they mean? They indicate the direction of the electric field at whatever point in space the field line is. So if I'm down here in the diagram for the positive charge, and if I look at a point in space along one of those field lines, the arrow gives me the direction of the electric field at that point. Also, they indicate the strength of the electric field, and this occurs due to the separation of the field lines in the diagram. The further apart the field lines are from one another, the weaker the electric field is, and conversely, the closer together that they are, the stronger the electric field. So for the positive and the negative point charge, you see that when we're close to the point charge, that's where the lines are closest together, which means that's where the electric field is strongest. And that agrees with our result for the point charge electric field, that it's proportional to 1 over the distance squared. One thing about these two diagrams for the positive and negative point charge, they're almost the same except for the direction of the arrows. And that makes sense again. Remember, the electric field is defined so that it points in the direction in which a positive test charge would feel a force. So no matter where we put the positive test charge near a positive charge, it would feel a repulsive force. And no matter where we put a positive charge in the vicinity of a negative charge, it would feel an attractive force. So the electric field lines then also are drawn originating at a positive charge or at infinity. And so if you look at these two diagrams below, the electric field lines begin on the positive charge. And if there's a negative charge and no positive charge around, then the field lines come in from infinity. If we put these two charges together, then the field lines would begin on the positive charge and end on the negative charge. And you may have seen these kinds of electric dipole field lines before. So that covers both of these 2 points. Field lines originate at a positive charge or infinity, and they end at a negative charge or infinity. What's really important is that field lines in a correctly drawn diagram never cross at any point in space. And you should think about why they don't cross. But remember that if the electric field lines indicate the direction of the electric field at points in space, if two field lines crossed, then that would somehow mean that the electric field at the point where they cross was pointing in two different directions at the same time. And that really would be nonsense. One more word about the uniform field. Remember that the strength of the field is indicated by the separation of the field lines. So if the lines are always the same distance apart, that means no matter where you are, the electric field has the same strength. And again, if they're parallel, and the arrows all point in the same direction, it means that the field always has the same direction. And that is a uniform electric field. So you may have occasion to draw these kinds of field lines, or at least to interpret them in your work, so make sure that you understand these rules. Now we're going to move on to talk about electric dipoles. Electric dipoles are nothing more than equal charges that have opposite sign and that are fixed at a certain position in space. So these negative q and positive q sit a distance d apart along, in this case, the x-axis. And this is important. We consider electric dipoles because they're really useful models for understanding the behavior of ionic molecules. Many molecules in nature form through the transfer of electrons from one atom to another atom. And in the process of transferring electrons, we end up with a negative charge and a positive charge. And if initially the atoms were neutral, then these two charges have to have the same magnitude. So the attraction between them is what holds the molecule together. So what we discover about electric dipoles is very relevant to the behavior of these tiny ionic molecules. The electric dipole moment, which is labeled by the vector p, is always drawn from the negative charge toward the positive charge. And it has, by definition, the value q times d, and in this case, because going from negative to positive is in the positive x direction, then it has the vector I hat. So we'll see why it has this definition a little bit later when we calculate the electric field produced by the dipole. But for now, here's the definition, and the units, of course, then are charge units times distance units, or Coulomb meters. Here's the example that I want to work through that will give us one of the important results from the textbook that we can use in understanding how an electric dipole influences another charge or perhaps another dipole. And what we want to do is calculate the electric field on the axis of a dipole, in this case a distance x away from the center of the dipole. So the dipole is composed of a negative q and a positive q centered on the origin, lying on the x-axis, and a is the separation distance from the origin to each charge. So point P is where we want to find the electric field produced by the dipole. The reason, of course, that it's not zero, because you might think that the field due to the positive charge and the field due to the negative charge might cancel out. But they don't, because the point P is closer to the positive charge than it is to the negative charge. So even though the two contributions to the electric field will be in opposite directions, as shown by the sketch, they won't cancel out completely. So part A is just to find the electric field on the axis of the dipole at point P, and then we want to show an approximate expression for that result, which is a handy one to use when we're dealing with electric dipoles. So here's how it works. You see again the sketch reproduced on this slide, and what we want to do is calculate the fields E minus and E plus and then combine them through the superposition principle to find the net field at point P. So the electric field at point P is E plus I hat minus E minus I hat, and since the two fields point in different directions, it's actually the magnitude E plus minus the magnitude E minus times I hat. So here is, remember, the expression for the electric field of a point charge, kq over the distance squared from the point charge, and very simply then you can see from the diagram that for the positive charge, kq is in the numerator, and the distance between the point charge and P is x minus a. That's the distance right here in the denominator. So it's x minus a squared. And E minus is kq over x plus a squared, because the negative charge is a distance x, right? It's from the origin to point P is x, and then you have to add in the distance a to get the separation distance. So those two look similar, but when we subtract them from one another, as the expression above shows how to do, we get that the net field is kq over x minus a squared minus kq over x plus a squared. And the strategy in combining these two is familiar, and we just want to get them over a common denominator. So when we factor out the kq, we've got these two terms that have different denominators. Well, the first term we're going to multiply the top and the bottom by x plus a squared. The second term we're going to multiply top and bottom by x minus a squared. And that gives us kq times x plus a quantity squared minus x minus a quantity squared over the denominator, which is now the product of the two individual denominators in the original expression. So we just have to expand x plus a squared and x minus a squared in the numerator, which is easy enough to do. The first term is x squared plus 2ax plus a squared. That's the first term. The second term is, and we subtract it, the second term is x squared minus 2ax plus a squared, but then we subtract all those, so we get minus x squared plus 2ax minus a squared. And lo and behold, the x squared terms cancel, the a squared terms cancel, the 2ax terms add together to give 4ax, which then gets multiplied by kq. So that takes care of the numerator, and the denominator, the x minus a squared times x plus a squared, when we multiply that out and cancel out certain terms, we'll see that it reduces, it simplifies to x squared minus a squared quantity squared. And so that just gets carried along in the denominator. So that gives the exact expression for the electric field at the point P, which is a distance x away from the center of the dipole. And now we can use the approximation when x is large compared to the size of the dipole. If x is large compared to a, then the denominator term, x squared minus a squared, becomes approximately just x squared. So then the electric field becomes 4kqax over x squared squared, or x to the fourth. And so that becomes 4kqa over x cubed, and if I just put in the I hat to indicate the direction, we get the correct direction. So since the electric dipole moment we defined just a minute ago as 2a, which is the separation distance of the dipole, times q, the charge on one of the charges, times I hat, then E can be written in terms of the dipole moment as simply 2 times the Coulomb constant times the dipole moment vector over the distance cubed. So that's the approximate expression for the electric field of a dipole that we'll use on some of the homework problems. And it's usually, at least it's often, a good approximation because molecules are so small. Those A distances are really small, so that if we're at all far away from the molecule, then we can apply this approximation.